Jai Hind, welcome to class of Analog and Digital Communication. So, we start with Unit 3 today, which is pulse modulation. So, before starting with actually pulse modulation, let's go through a little overview of what modulation is. We all are aware of. When we alter the characteristics of a very high frequency carrier wave with respect to the instantaneous value of message signal, that process is called as modulation. And when we are specifically talking about pulse modulation, then here my carrier wave would be pulse in nature. It is a type of modulation in which the signal is transmitted in the form of pulses. So the carrier used here isn't a high frequency sinusoid, it is a high frequency train of pulses. So the modifications that we do in the carrier is we do modifications in the pulses. So these high frequency pulses will somehow imitate my message signal or make some changes in its own appearance so that it carries the information that my message signal has. So it can be used to transmit analog information. In pulse modulation, continuous signals are sampled at regular intervals. So there has to be rule for it. There has to be regular intervals at which it has to be sampled. All these terms like sampling, regular intervals will take one by one when we proceed in the lecture. So pulse modulation can be classified into mainly two types, analog and digital. It indicates the sample amplitude is infinitely variable, and in digital, sample amplitude at the nearest predetermined level. So as the name suggests, analog and digital, we have infinite number of sets in analog, and in digital we have finite sets. So with the help of a block diagram, I'll show the basic classification of modulation techniques. If we classify modulation techniques in analog and digital, so even before classifying it into analog and digital, we can classify it on the basis of what kind of carrier waves do we use. If the carrier wave used is continuous in nature, that kind of modulation is called as continuous wave modulation. Whereas if the high frequency carrier is a pulse train instead of a continuous wave, that kind of modulation is called as pulse modulation. Right? So if we go with continuous wave modulation, we have amplitude modulation and angle modulation. These two are covered in unit 1 and 2 previously, right? Amplitude modulation, where the characteristics of a high frequency carrier wave is altered with respect to the instantaneous value of the message signal, right? Where the amplitude of the high frequency carrier is altered with respect to the low frequency message signal. And in such kind of modulation, in amplitude modulation and angle modulation, the message signal that we consider is always considered to be a voltage signal, right? So as we know that my wave, a pure sinusoid can be written as A sine omega t. My wave has these two characteristics, amplitude and angle. When I vary the amplitude of the carrier wave, that is called as amplitude modulation, and when I vary the angle, that is called as angle modulation. Angle modulation is further classified into frequency and phase modulation, right? And if I now in this unit we are focusing on pulse modulation. So here, as here my carrier was a high frequency continuous wave, here my carrier will be a high frequency train of pulse, that is a fast moving train of pulse, right? So it can further be classified into analog modulation and digital modulation. We have pulse amplitude modulation, pulse width modulation, and pulse position modulation, which comes under analog modulation. And we have pulse code modulation and delta modulation as digital modulation. Here my message signal will be analog in nature and my carrier will be high frequency train of pulse. So let's take these things one by one, right? So now, as we know that we are going to talk about pulse modulation in detail, So let's first of all get the real meaning of pulse modulation and why are we studying pulse modulation. We know that all the signals available in nature are analog in form, but in today's life we are using the communication in its digital mode. There are several reasons for switching or moving from analog to digital communication, right? So when we switch from analog to digital communication, there comes an intermediate stage of pulse modulation. That's why we are studying pulse modulation. So first of all, let's take one by one reason why do we need to switch from analog to digital communication. Number one reason is we need lesser memory, right? My analog signal would require infinite set of values. So when I store this, I would require a lot of memory. If I talk about digital communication, they'll have finite set of values, right? So one of the foremost reasons for switching to digital communication is memory. Second major reason is in noise interference. My analog communication is more prone to noise, whereas my digital communication is more immune to noise. And third most important reason is we do have n number of coding schemes available for digital mode of communication. Right? So these are the three major reasons. Apart from it, there are n number of reasons for switching from analog to digital communication. Now the question is, when most of the signals available in nature are analog in form, then there must be the need of conversion of analog signals into digital, right? And when we convert our analog signal into digital signal, there are steps that we need to follow. Number one step is called as sampling. Number two is quantization, and number three is encoding. So when we need to convert our analog signal into digital signal so that we can further use digital mode of communication, then we need to follow these steps. So sampling, what is sampling? It is the process of converting a continuous time signal into discrete time signal. Let's see what is a continuous signal. This is a continuous signal. If I take it, this is the time domain and this is the amplitude domain, which is voltage. At every instant of time, it does have some voltage value. And if I have to take this set, I have infinite set of values, right? So here the time axis is also continuous, the voltage axis is also continuous. While we approach from analog to digital mode, finally what do we get as binary bits, right? We have finite set of representation levels, either 0 or 1, or maybe if we use die-bit combination, then 4 levels. If we use tri-bit, then 8 levels, and so on. But these are countable. When we need to move from continuous in time and continuous in amplitude to discrete in time and discrete in amplitude, then sampling will convert a continuous in time signal into discrete in time signal, right? And the next process, quantization, will convert a discrete time signal further into discrete amplitude signal, right? So with the help of sampling, we are just discretizing the time domain. What it is? The figure that I'll show, it will indicate a continuous time signal and a sample signal. Let's see how does a sample signal looks like. So if this is a continuous time signal, after sampling, it must look like this. So if I'm representing it with xt, my signal is a function of time here. xst represents that I have samples at fixed interval of times. So somehow I am reducing the reducing infinite sets into some finite set, right? So the time domain was continuous there. I had infinite set. Now I have finite set of time domain values, right? So sampling does that for me. Now, a signal is a periodic train of pulses having unit amplitude sampled at equal interval of times. So it could be understood as simple as that. Taking samples, instead of taking the complete signal, let's take this portion. After some time interval, let's take this portion, let's take this portion, let's take this. So I'm taking samples of the signal, right? So these samples could be represented like this, or maybe like this, or maybe like this, right? So depending on how do we represent it, we have sampling types that I'm going to discuss after few slides. So this data is transmitted at time instant Ts. Every sample is processed after sampling time interval Ts, and the carrier signal is transmitted at the remaining time. Now, it's not just that I can make n number of samples as per my desire. No, it has to follow specific rule. So sampling theorem bounds that. What the sampling theorem says? The rate of sampling should be such that the data in the message signal should neither be lost nor should it get overlapped. What does it mean? When from this I am making this at receiver side, I'll have to go back again from this to this. And when I recover my signal back or reconstruct my signal back, I should be able to accurately retrieve it back. More number of samples if I take, I'll have closely spaced values, and plotting that will give me close to accurate value. If I take less number of cycles, then the probability of error will increase, right? So there has to be a rule that will define that how many samples should I take for what frequency of message. So sampling theorem states that a signal can be exactly reproduced if it is sampled at a rate fs which is greater than or equal to twice the maximum frequency. Sampling theorem says my fs must be greater than equals to twice of w, where W is my message bandwidth. Let's see. To discretize a signal, the gap between the samples should be fixed, which is said as sampling time interval, which is represented by Ts, and sampling frequency, Fs must be equals to 1 by Ts, where Ts is the sampling time, Fs is the sampling frequency. And as per sampling theorem, my Fs must be greater than equals to twice of W, right? What does it mean? Let's suppose I'm taking a message signal of 5 kilohertz. Then how many number of samples do I have to make? A 5 kilohertz signal means in 1 second there will be 5,000 cycles. For a signal with 5,000 cycles per second, we will have to take at least, which is 10,000 samples per second. So for a signal to be represented nicely and to be reconstructed back accurately, I have to take minimum twice the sampling frequency. I have to sample it at a frequency, at least at a rate which is twice the maximum frequency content of my message. So I have taken this example. If I have a message signal of 5 kilohertz, that means it has 5,000 cycles per second. For such signal, I have to sample it at least at 10 kilohertz sampling frequency. That is, I have to take minimum 10,000 samples per second. Then that signal will be represented accurately and I'll be able to reconstruct back my signal accurately. This is what sampling theorem says. And if I sample it at minimum sampling frequency, then that rate is called as Nyquist rate. If the rate of sampling is called as when I sample at minimum sampling frequency. This is the minimum number of samples. Maximum, practically we sample at a rate much higher than Nyquist rate. Right? The sampling theorem is also called which is also called as Nyquist theorem, delivers the theory of sufficient sample rate in terms of bandwidth for class of functions that are band limited. Now for continuous time signal ST, the band limited signal in the frequency domain can be represented as this. This is how I can show a band limited signal minus WTW, the frequency band exists, right? If I sample it at a rate higher than 2W, the question is, why do we have to strictly follow sampling theorem? What if I don't follow sampling theorem and I sample at a rate lower than sampling theorem, lower than Nyquist rate? That if I keep Fs less than 2W, what will happen? So before that, let's consider the case. If I sample it at a rate higher than 2W, then this is how after sampling it will look like. If the signal is sampled above Nyquist rate, the original signal can be recovered like this. The following figure, this above figure, explains a signal if sampled at a rate higher than 2W in frequency domain. In frequency domain, I am able to retrieve back the signal accurately. If I sample it at a rate less than 2W, what will happen? Overlapping. If the signal is sampled at a rate less than 2W, then sampled signal will look like this. That is, what is this? My high frequency signal is somehow taking the identity of my low frequency signal. And this effect is called as aliasing. We can observe from the above pattern that overlapping of information is done, which leads to mixing up of, when it mixed up, some information is lost at the time of recovering or reconstructing. This unwanted phenomena of overlapping is called as aliasing. Now, aliasing can be referred to as the phenomena of a high frequency component in the spectrum of a signal, taking on the identity of a low frequency component. What is aliasing? When a low frequency component takes identity, taking on the identity of, when a high frequency component takes the identity of a low frequency component in the frequency spectrum of the sampled version, that is called as aliasing. And this isn't considered good for communication. So if we are sampling at Nyquist rate, f is equals to 2W, what will happen? The sampling of here, my sampling time interval is strictly following this, right? My sampling time interval between two samples is 1 by 2W, right? Hence, the sampling of the signal is chosen to be at the Nyquist rate or at a rate higher than Nyquist rate. As it was stated in the sampling theorem, if the sampling rate is equal to twice the highest frequency, that means f is equals to 2W, then what will happen? I'll get sampled version will look like this. This is how my sample version look like at the time of reconstruction. Okay? The result will be as shown in the figure. Here, see, these are just touching the edge of each other. If I sample at a rate higher than sampling frequency, they will be separated and no overlapping. At sampling frequency, this happens. Lower than this, overlapping, right? So we have to sample at a rate equal to or higher than Nyquist rate. Now, these are the three. Let's give it a look again. At a rate higher than Nyquist rate. Right? At a rate lower than Nyquist rate. This is the case when Fs is less than 2W. Right? This is the case Fs is greater than 2W. This is the preferred one. This is what we do not prefer, as the identity of low frequency signal and high frequency signal is mixed, and because of this overlapping, we lose some data, right? So this isn't considered good. It's called aliasing effect, and this is what we get at a rate when we sample at Nyquist rate. Now, after this, so this is clear as of now that we have to strictly follow sampling theorem in order to make our communication successful, so that when we retrieve back our signal at the receiver and reconstruct it back, we are able to retrieve back our signal most appropriately. And what are the ways to prevent it? We may use low pass filters, which are also called as anti-aliasing filters before sampling. So those low pass filters will help me prevent aliasing effect, right? So to prevent aliasing, we may use some low pass filters. After this, various type of sampling. Let's take a look of how my sampling looks like. There are three types of sampling techniques: impulse sampling, right? Natural sampling, and Impulse sampling is also called as instantaneous sampling. Another type is natural sampling and flat top. What is impulse sampling? It can be performed by multiplying input signal xt with impulse train of period t. Here the amplitude of the impulse changes with respect to amplitude of the input signal. This is also called as idle sampling. So we may call it as impulse sampling or idle sampling. You cannot use this practically because pulse width cannot be zero. Let's take a look at the picture, then we'll come back to this slide. If this is my continuous wave, right, this is an impulse train. So if I simply multiply this with this, what do I get? The amplitude of this will be kept as per the voltage level of the signal, and I'll get such kind of output, right? So these are my impulse sample or idle samples, right? So this is a mere representation of this signal in the form of impulse samples, whereas we cannot use it practically. Why we cannot use it practically? Because the pulse width cannot be zero, and the generation of impulse train is not possible practically. The output of the sampler is given by this, right? So this pulse width cannot be zero. So practically, this is just a kind of classical study that we do. We usually don't perform it for practically converting a signal into its corresponding samples. If I talk of natural sampling, it is similar to impulse sampling, except the impulse train is replaced by pulse train here, right, of time period t. So let's see, if this is my input signal, message signal, here the impulse train is replaced by flat top pulses, and if I multiply this, what do I get? Right? And I represent my waveform like this. So this is what is represented. Right? This is what is represented. So this is how I may represent my natural sampling. This is quite used a lot. After that, flat top sampling. What is flat top sampling? During transmission, as noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in the form of flat top. See, if I have this amplitude variation which is continuous in nature, see, here my samples are appearing at every sampling time interval. After this is Ts. My sample is appearing after Ts time gap. But I have discretized the time domain, but amplitude is still continuous. From this value to this value, I can have infinite set of amplitude values. If I can have infinite set of amplitude values, then the noise will of course affect this. Instead of this, why not use a flat top to represent the complete sample so that I remove those errors caused by noise, distortion caused by noise. So if the pulse is in the form of flat top, this noise can be removed. Here the top of the samples are in constant amplitude form. Hence, it is called as flat top sampling. Let's see how it looks like. If this is my continuous time signal and I use flat top samples and I replace those continuous amplitude samples with these flat tops, I'll get these kind of flat top samples. So these are most commonly used kind of samples in communication, right? So that's it for today. We have covered, we have gone through the introduction of, let's give it a look again. What is pulse modulation? When instead of continuous high frequency continuous wave, we use fast moving pulses. That kind of modulation is called pulse modulation. We have analog and digital, PEM, PWM, PPM, and in digital we have PCM and delta modulation. So before starting with PAM, we have seen how an analog signal is converted into digital and how samples are generated. So what is sampling? How the sample signal looks like. What is sampling theorem? It says Fs must be greater than equals to twice of Fm, twice of W, where W or Fm is the maximum frequency content of message. Then how do I represent my band limited signal? If I do sampling at a rate higher than 2W, at 2W and lower than 2W. So how does my waveform looks like after this? types of sampling techniques we have covered. Impulse, which is also called as idle sampling, natural sampling, and flat top sampling. Flat top sampling is the most used one. So that's it for today. These are the references I've used.